In this problem we have a heavy box that's supported in its lower left corner by a ball and socket joint and also supported by 3 ropes. Additionally, we have 2 forces down here. There's a 600-pound force that acts in the z direction, and there's a 900-pound force that acts downward in the y direction. We also know the dimensions of the box. We know it's 3 feet by 4 feet by 1.5 feet tall. The weight of the box acts downward at its center of mass. Let's call the ball and socket joint point A. We'll call this rope BD. This rope we'll call CE, and this rope we'll call CF. This is a demonstration of what a ball and socket joint actually does. It simply prevents movement in the x, y, and z directions, but it doesn't provide a moment in either of those directions. So it does allow rotation about all 3 axes. Whenever a constraint like a ball and socket joint prevents movement in a particular direction, it means it can provide a force in that direction. So the ball and socket joint can apply a force upward in the y direction, it can apply a force in the x direction, and it can apply a force in the z direction. But because the ball and socket joint is frictionless, it can't produce a moment in any of those directions. We'll label the components of the ball and socket joint AX, AY, and AZ. One thing to consider are the number of unknowns that we have in the problem. We'll want to make sure that we can actually solve this thing. So 3 unknowns, we've got AX, AY, and AZ are the first 3 unknowns. Second unknown is the force in rope BD. The 5th unknown is the force in rope CE, and the 6th unknown is the rope in CF. For 3-dimensional problems, we can write a total of 6 equations. The first equation is the vector sum of F must be equal to 0, and the second equation is the sum of moments about any point must equal 0. And for any point, in this problem, we'll choose point A just for convenience. If I wrote them out explicitly in scalar form, here are my 6 equations, the sum of forces in the x, y, and z, and the sum of moments in x, y, and z. So 6 equations and 6 unknowns, which suggests that we can actually solve the problem. But one other thing we need to look for is the fact that none of these forces is concurrent. And what that means is that because all of our forces are sliding vectors, it means that we can't have another force, for example, at this corner, 2 unknowns in these directions. They're sliding vectors, so mathematically they look identical, and you'll have an equation that you can't solve. We still have one other issue, however, and that's the fact that all 3 of these are ropes, and ropes can't withstand a compressive force. They can only withstand tension. And if I look at this, we've also got a downward force here, and what that would have a tendency to do is rotate this box about the ball and socket joint. And in doing so, we'll see that the rope on the far side can't support that type of motion. I can't show it in the animation, but in reality, the rope would just go slack, and it can't support that. And if I looked at it from this angle, here's the downward force, the downward motion, and we see the rear corner of the box would come up, and this rope would go slack. So in reality, this could not be a rope. It would have to be a linkage of some sort. BD would have to be some kind of metal. So maybe I'll just shade in BD in black to show that it's a linkage or something that can support a compressive force. But for the sake of the free body diagrams, let's assume it's under tension, and let's assume that the force acts upward. And if we get a negative answer for the force in BD, it does show mathematically that that member is indeed under tension or compression. Well, let's solve this problem by writing our first 3 equations out, just the sum of forces in the x, y, and z direction. From this perspective, it's not terribly difficult to write it. I see I've got AX acting in the x direction, but no other forces, so that says that AX has to be 0. The sum of forces in the y direction, of the vertical, we've got AY acting upward. We've got the force of BD acting upwards. Assuming that it's under tension, we'll find that it's not. It's actually under compression. We've got FCE acting upwards, and we've got this downward force of 900 pounds, and we've got weight also acting downwards. In the z direction, I've got, again, the constraint AZ. I've got a 600-pound force, and I've got the force of this rope CF acting in the negative direction. To write out the sum of moments in each direction, I think it's easiest to draw 3 views of the box. The first being with the x-axis pointing straight out of the screen, second with the y-axis out, and the third with the z-axis acting straight out. So let's start by drawing it with the x-axis coming out. And if we sight down this axis, I've got FBD and FCE are both in the same plane, FBD being behind FCE. I've got FCF acting to the right. I know that here's my downward force of 900 pounds, my force acting in the positive Z direction of 600 pounds, and I've also got the constraints for the ball and socket joint. So here I've got a Y acting in the upward direction, and I've got a Z acting in the positive Z direction, or to the left. And from this perspective, AX acts out of the screen, so we don't draw it from this perspective. And then finally, we've got the weight acting downward at the center of mass. So to write out our fourth equation in scalar form, we've got the first force we've got is a 4-foot lever arm, a counterclockwise moment due to FBD. We've got a 4-foot lever arm multiplied by FCE, and we've got a clockwise moment for FCF with a lever arm of 1.5 feet, and finally a clockwise moment with a lever arm of 2 feet for the weight of the box. And we'll just replace mg with the variable w because we're dealing with weight, not the mass. If we look straight down on the box with the y-axis coming out, we've got the reaction force AX and the reaction force AZ acting in the positive x and the positive z directions. Our fifth equation, which is the sum of moments in the y direction, is as shown. Counterclockwise moment from FCF with a 3-foot lever arm, and a clockwise moment of 600 pounds also with a 3-foot lever arm. And finally, our sixth equation is the sum of moments about the z-axis. We can get that by looking straight down the z-axis. And here from this perspective, we have AX acting in the x direction and AY acting in the y direction. We've got a counterclockwise moment for FCE with a lever arm of 3 feet, a clockwise moment due to gravity of 1.5 feet, and a clockwise moment of 900 pounds with a lever arm of 3 feet. So these are my 6 equations and 6 unknowns, and for a given value of W, we could solve for all 6 of these forces. And here's what a graph of these would look like. FCE gets larger as the weight of the box, as we increase the weight of the box, and that's because FCE is supplying the vertical component of the force that supports the weight. What we find is that FCF doesn't change with weight, and FBD doesn't change with weight. We also see that FBD is under compression, that's a negative value of the force as we expected from the animation to begin with. So FBD could not be a rope, it would have to be a solid linkage to support a compressive force. If I add a Y, the vertical reaction of the ball and socket joint, we see that it supports more and more weight as the weight of the box is increased. And in all cases, we find that AX is equal to 0 and AZ is equal to 0.